Welcome to the deep dive. Today, we're going to be looking at two textbooks you sent us.
Okay.
Communication Systems Engineering by Proakis and Salehi.
Right.
And Wireless Communications by Goldsmith.
Okay.
So we're going to talk about digital communication.
Yeah.
Have you ever thought about how a message goes like across the room or to a spacecraft millions of miles away?
Right.
It's kind of amazing, right?
It is, yeah.
The magic of it is, whether we're talking about like old school radio or the latest Wi-Fi technology, it's all based on the same fundamental principles.
That's right. Digital communication systems might seem kind of like science fiction-y.
Right.
But they're built on solid engineering principles that we can break down.
Okay.
For everybody.
All right. Let's start with the basics.
Okay.
The building blocks of a digital communication system. And Proakis and Salehi have this diagram, figure 1.2,
right,
that shows us the key players.
It's a visual roadmap for how the information flows from a source, which could be anything from like a person speaking or a computer generating data all the way to the intended recipient.
Okay. One of the things that really stood out to me was the source encoder. It's all about efficiency, right?
Exactly.
Kind of like when you're packing a suitcase for a trip. You don't want to take your entire wardrobe with you.
You got it.
You want to pack light.
Right.
So the source encoder is like this master packer.
Yeah, it eliminates redundancy to streamline the transmission.
Oh, okay.
So instead of sending every single letter of the alphabet, we just send the letters that we need to convey our message.
Right.
You know?
That's pretty smart.
Yeah.
Okay, and then once the information is tacked down, it's converted into the language of computers. Binary digits.
Yes. Yeah. And then those binary digits are processed.
Okay.
And modulated.
Modulated.
It's like attaching our message to a carrier signal.
Okay.
A wave that can travel through the air or through cables. And then at the receiving end, the process is reversed.
Okay.
We demodulate to strip away the carrier wave, and the source decoder unpacks the message.
So it's like a perfectly synchronized dance.
It is dance.
Of encoding, modulating.
Yeah, transmitting, demodulating.
Transmitting, demodulating, and decoding.
And decoding, that's right.
Wow. Okay, so let's talk about the signals themselves.
Okay.
Proakis and Salehi talk about energy and power.
Yeah.
What's the deal with those?
Okay, so understanding energy and power is really key to understanding how signals work.
Okay.
So imagine this energy is like the total fuel in your car.
Okay.
And power is the rate at which you burn that fuel. So some signals, like a short burst of data, are like short trips.
Right.
They use up a fixed amount of energy.
Got it.
Other signals, like a continuous radio wave, are like a long road trip.
Okay.
They require continuous supply of power.
Oh, so all those radio waves we're listening to right now, those are power type signals.
Right. They're power type signals.
It's like a constant stream of energy.
Right.
Carrying music and news.
Right here.
Even this podcast to our ears.
That's right. It is.
Pretty cool, huh?
It is, yeah. And understanding this difference is really important when you're analyzing signal behavior and designing communications systems. You know, it's like knowing whether you need a powerful engine for short bursts of speed or a fuel-efficient one for long journeys.
Gotcha. Okay, so now let's get a little more complex.
Okay.
How about angle modulation?
All right.
Proakis and Salehi go into frequency and phase modulation. What's the big idea with that?
So think about a carrier signal as like a steady tone.
Okay.
Angle modulation is a way to encode information by changing the tone of that carrier signal.
Okay.
So in frequency modulation, FM, it's like changing the note.
Okay.
But in phase modulation, PM, it's like changing the rhythm.
Got it.
Right.
So FM is like the pitch and PM is like the timing.
You got it. Exactly.
And this manipulation offers some benefits.
Yeah, it does.
Especially when it comes to noise immunity.
Right. That's why FM radio tends to sound clearer than AM radio.
Even in areas with weak signals.
Exactly.
That's fascinating. Okay, so our sources also dive into randomness and probability.
Yes.
Why do those concepts matter in digital communication?
Okay, so they're essential because communication channels are rarely perfect.
Okay.
So imagine trying to read a message that's written in sand on a windy beach.
Okay.
The wind represents noise and unpredictable conditions.
Right.
And it can make the message hard to decipher.
Yeah.
That's where probability comes in. It helps us to model and understand this uncertainty.
So we're kind of battling the elements.
We are.
Trying to make sure the message gets through.
That's right.
Intact.
And one of the most important tools in that battle is the bell curve.
Oh, the bell curve.
Or the Gaussian distribution.
Okay, we all know the bell curve, but what makes it so special for communication?
The Gaussian distribution is remarkably good at describing noise in communication channels.
Okay.
So think about static on a radio.
Right.
Or errors in data transmission. This Gaussian distribution helps us to understand and mitigate these issues.
Wow, so this simple bell curve is like this big player.
It is. It's a cornerstone of communication engineering.
In keeping our messages clear.
That's right.
Now to add another layer of complexity.
Okay.
We've got random processes.
Yes.
What are those?
Okay, so random processes are like random variables.
Okay.
But they unfold over time. So think about fluctuating stock prices. Or changing weather patterns.
Right.
These are random processes in communication. Fading signals, interference, and even message arrival times can be modeled as random processes.
So it's not just about random events,
Right.
but how they change over time.
Exactly.
Okay, that seems pretty important.
It is. Think about fading signals. Their strength changes randomly over time as they travel through the environment. That's a random process. And understanding them helps engineers build systems that can adapt and maintain reliable communication.
So we've got the basic components of a communication system. We've got signals with their energy and power.
Right.
And we've got randomness and probability helping us to make sense of the chaos.
Right.
But what happens when those signals run into tricky situations?
Right.
Like when they're trying to get through a concrete jungle or a forest.
That brings us to a major hurdle in wireless communication.
Go.
Multipath fading.
Oh, and this is where Goldsmith's expertise comes in.
Indeed.
Okay.
Yeah.
Awesome.
Yeah.
Welcome back to our deep dive into digital communication.
You got it. We've laid a solid foundation, exploring those building blocks and the challenges.
Right.
Now it's time to uncover some of the techniques that make reliable communication possible.
Yeah. And I'm hearing whispers of some pretty revolutionary solutions.
Let's start with MIMO systems.
MIMO.
It stands for multiple input, multiple output.
Okay.
And Goldsmith explains this in our sources.
Okay, MIMO. That sounds impressive.
Yeah.
But how does it actually work?
So imagine instead of just having one antenna trying to shout across a crowded room, you have a whole team of speakers, all perfectly synchronized, each sending a slightly different part of the message.
Oh, okay, so it's like a coordinated choir.
Exactly.
Each voice blending together.
Yeah, to create a richer, more robust sound.
To create a more robust sound, okay.
By using multiple antennas at both the transmitter and the receiver, MIMO achieves two really remarkable things.
Okay.
First, it combats fading.
Right.
Like having multiple backup routes for our signal.
Right, like that diversity idea?
Exactly, precisely. But MIMO goes even further.
Okay.
It can dramatically increase data rates.
Oh, wow.
By creating parallel data streams.
So we're not just making the signal more reliable.
Right.
We're also making it faster.
We're turbocharging the speed.
Okay, that's incredible.
MIMO is a key technology behind the really fast speeds of Wi-Fi.
Right.
And 4G and 5G cellular networks.
Okay, awesome. So let's move on to another technique.
Okay.
Multi-carrier modulation.
Yes.
So from what I gather, it's kind of like dividing a heavy load into smaller, more manageable packages.
You got it.
Making transport easier.
Multi-carrier modulation, particularly OFDM.
OSDM.
Orthogonal frequency division multiplexing.
Okay.
It's all about slicing and dicing the data into multiple subcarriers.
Right.
Each carrying a small chunk of information.
So instead of sending one big, bulky signal that's susceptible to all this interference, we're sending a fleet of smaller, more agile signals.
A perfect analogy.
That can navigate those obstacles more effectively.
Yes, and because each subcarrier has a smaller bandwidth, it's less affected by frequency selective fading. Those pesky echoes we talked about.
Right, so they can kind of weave through those challenging environments.
Precisely.
Without getting too distorted.
And by transmitting these subcarriers simultaneously, OFDM achieves impressive data rates, making it a key technology for high-speed communication.
Okay, I'm officially impressed.
Good.
But we also have spread spectrum.
Yes.
Which sounds a little bit like a spy movie.
Well, In a way, it is about hiding in plain sight.
Okay.
Spread spectrum techniques involve spreading the signal bandwidth.
Okay.
Much wider than necessary.
Now, why would we want to use more bandwidth than we need?
It's all about gaining an edge in security and interference mitigation.
Okay.
So imagine whispering a secret message in a crowded room by spreading your voice over a wider range of frequencies. It becomes harder for others to pick it up and for background noise to interfere.
So it's kind of like we're disguising our signal.
Exactly.
Making it blend in.
Making it blend into the background noise.
With the background noise.
And this is why spread spectrum is used in military communications.
Oh, wow.
GPS and even some wireless standards like Bluetooth.
Okay, so this deep dive is really opening my eyes to the incredible ingenuity.
It is remarkable.
Behind digital communication.
Yeah.
We've covered some mind-blowing techniques from MIMO to spread spectrum.
We have.
It's amazing how engineers are constantly pushing the boundaries.
It is truly remarkable, but before we get too carried away, there's another essential aspect. We need to address error control coding.
Error control coding. What is this?
So remember all that talk about noise and interference potentially corrupting our signals? Well, error control coding is a powerful set of techniques designed to detect and correct those errors.
Also, it's like a spell checker.
You got it.
For our digital messages.
In a sense, yes, these codes add redundancy to the data. And if errors occur during transmission, the receiver can use this redundancy to identify and often correct the mistakes.
So it's like a safety net.
Exactly.
For our data.
Preventing those pesky errors from ruining our message.
Okay, so there's a whole toolbox.
There is.
Of error control coding techniques.
A whole toolbox.
Wow. It sounds like error control coding deserves a deep dive of its own.
It certainly does, but for now, I think we've covered a lot of ground.
I agree. We've gone from the fundamental principles of digital communication to all these ingenious techniques that make it all possible.
That's right. It's been quite a journey.
It has been. And as we wrap up this part of our deep dive, I'm curious to know what the future holds.
Well, buckle up because we're about to explore those exciting possibilities and the challenges that come with them in the final part of our deep dive.
Stay tuned, folks.
Yeah.
We've got more fascinating insights coming your way.
We do.
Welcome back to the final part of our deep dive into digital communication.
We've explored the building blocks and the ingenious techniques. We even dipped our toes into error control coding. But as we hinted at before, the journey doesn't end there. The future of digital communication is full of possibilities and challenges.
For sure.
One of the most pressing issues is the ever-growing demand for higher data rates. As we connect more devices and consume more data-intensive content like streaming high-definition video, it puts a lot of strain on existing infrastructure.
It's like a highway getting more and more crowded during rush hour. We need to either widen the lanes or build new routes.
A perfect analogy. So engineers are exploring ways to address this. Things like using higher frequency bands like millimeter waves to developing even more sophisticated multiplexing and modulation techniques.
And with the rise of AI and machine learning, I bet those fields will play a big role in optimizing these systems.
Absolutely. AI and ML can help design smarter, more adaptable networks. That dynamically allocate resources and optimize signal processing. They can even predict and mitigate congestion before it becomes a problem.
Wow. So the future of communication is as much about software as it is about hardware.
Yeah, I think so.
But as we strive for faster speeds, we can't forget about security. With our reliance on digital communication, protecting sensitive information from cyber attacks is super important.
You're absolutely right. It's not just about sending data quickly and efficiently. It's also about sending it securely. This is where cryptography and quantum communication come into play.
Those sound like some serious security measures.
Cryptography involves scrambling information in a way that only authorized parties can decipher it. And quantum communication takes security to a whole new level by using quantum mechanics to create virtually unbreakable encryption.
So we're talking about like spy-level security for everyday communication.
These advancements are really important in a world where our personal information and financial transactions and even critical infrastructure rely on secure digital communication.
It's amazing to think about how far we've come.
It is.
And how much potential lies ahead.
Yeah.
This deep dive has given me a new appreciation for this complex and fascinating world of digital communication.
It's truly a testament to human ingenuity.
It is.
From the basic principles to the cutting-edge techniques. It's clear that communication is always evolving.
And it's exciting to think about what the future holds.
Well, on that note, I think we've reached the end of our deep dive.
Thank you for joining us on this journey through the world of digital communication.
We hope you've gained a deeper understanding of how it all works and all the amazing innovations that are shaping the way we connect and share information.
And remember, the world of communication is always changing.
It is.
So stay curious and keep exploring.
Until next time.